A confirmation for the audio, please, guys. If you are able to hear me out perfectly well, kindly confirm the same. Thank you. So, hello, a very warm good afternoon to all of you, and welcome to Baiju's Exam Prep IAS. Welcome to another session and another weekend of geography, where finally in this weekend we shall be endeavoring to complete and finish the entirety of the portion of geomorphology and entering into the portion of climatology as well. Now, in the past week, what is it that we have discussed? So basically, we had initiated with the very basic concepts about what do we understand by the planet and the rotation, the movement of the planet around the sun. We looked at certain complicated concepts as well, such as Milankovitch cycles, and we looked at the reason that why is it that we have different length of day and night in between the different seasons. That is largely attributed to the tilt of the planet on its axis. We looked at the reasons why you have various ice ages and interglacial periods which are experienced with the help of Milankovitch cycles. And then we moved on into the interior of the planet, the rocks, the different types of rocks, and also the continental drift theory. Now, continental drift theory is one of those that we had taken a look into detail of it. And here, just to give you a quick recap of what we studied in the theory of continental drift. So here, we looked at, first of all, the evidences. So, first of all, what was the postulation of continental drift? What was the theory in itself? Now, the theory talks about the fact that you had one supercontinent with the name Pangaea, and you had water body surrounding that supercontinent, and that was Panthalassa. So, we had the situation where one supercontinent Pangaea surrounded by Panthalassa. Okay. And then we talked about the fact that it was Pangaea which broke into different parts. So Pangaea here broke into, first of all, Laurasia and Gondwana land. Now, the portion of Laurasia that we talk about, that included the portions of North America, included the portions of Europe, northern part of Asia, Greenland, everything was included in that. And in Gondwana land, you had Antarctica, you had South America, Africa, India, and Australia. Now, then further broke into different continents. Into different continents. Now, then, here, this theory was basically postulated and supported by various different evidences. So, which were the evidences which supported the theory? So, you had various different evidences. Now, the evidences were, first of all, the jigsaw fit of the continents. Then, other evidences were, for example, we also had the conditions where geological origin of rocks, Okay. We also looked at the the evidences which were pointed out where tillite deposits, or in general, it can be included in the larger point of glacial evidence. So first, placer deposits, then glacial evidence, and in the form of glacial evidence, we had tillite deposits as well as glacial striations. Then after that, paleontological evidence. So based on these evidences, the theory was postulated that at one point of time, all the continents would have been one, and they have then bifurcated and trifurcated and divided themselves into different portions, into different parts. Now here, after this, we also took a look at the assumptions made by Wagner. So what were the assumptions? Assumptions were about the interior, that is, continents float freely over oceans or over seama. And he assumed that seama represented ocean floor. And these were the assumptions based on which he basically gave two reasons that why this land is splitting and moving into two different directions. So the reasons were two, and what were those? First reason was to prove westward drift of continents. So in order to prove that, he gave the reason of tidal force generated by moon. Moon and sun. The second reason that he gave was in order to explain the movement away from poles. So movement away from poles. And for this, he gave the reasoning about a combination or combined effect of centrifugal force and force of buoyancy. Okay, this is what we had studied the previous weekend, and the entirety of the continental drift theory can be restricted, can be understood, and a note can be made in this one page itself. So why I have provided this recap is so that you get an idea, and all those of you who ask questions that how is it that we should go about and approach note making exercise and so on. So this is something which you can take in as an example, as a kind of a template, and that is how you can prepare your short notes, ideally for any kind of or any portion of the subject that you study, any subject that you come across. You can basically concise the portion that you have studied in this brief note. Now, what it will help you to do is, it will help you to be able to write, if needed, 150 words, if needed, 250 words, if needed, even 300 words out of this particular topic. So that is the ability you need to inculcate. Okay, so here basically if you will look at the type of questions, this is one of those areas where UPSC very frequently tends to ask questions as well. Very frequently UPSC will ask you question both in general studies as well as in the portion of optional. It will be asked about the continental drift theory, the evidences which indicate to the continental drift theory. All of that is asked by UPSC repeatedly. So, for example, take a look at the previous year question which was asked in the mains. Now, this is for 150 words. 10 marks. So, here the question is, what do you understand by the theory of continental drift? Discuss the prominent evidences in its support. Okay. Now here for answer writing, few of the things you have to keep in mind when we talk about answer writing for the subject of geography. There are a few things that you have to keep in mind. Okay, first of all, understanding the basic requirement of the question, right? What is it that the question is asking? The main question, and you should be able to be in a way discern that what are the subparts. What is the main question? What are the subparts and subparts? So, for example, in the above given question, here the basic question, the main question is, what do you understand by theory of continental drift? The sub part is discuss the prominent evidences. Okay, so in the introduction, when you are writing an introduction for the answer, introduction always has to address the main question. Always address the main question in your introduction, and introduction should be between 25 to 35 words, not more than that. Okay, if you write beyond that, there is no point of having an introduction anymore. So that should be your introduction. For example, what is the introduction that you will write here? So here you can write an introduction that the theory of continental drift provided by Alfred Wagner talked about the existence of one large supercontinent named Pangaea and the existence of one large superocean called Panthalassa. That Pangaea, or after that, you can straight away write that this theory of continental drift talked about the present position of continents and oceans as a result of the drifting of the continents. Now, this theory was supported by various different evidences. That is your introduction. Then after that, in the body portion, in the portion of the body, you have to address the main points, the subparts, and everything else has to be included. So for here, continuity from introduction is important. Continuity from introduction is very important. For example, let's say I have finished the introduction with a sentence that the theory was supported by various different evidences. Now here, initially when you write the body, the evidences can be classified into various different proportions and various different types. So you can talk about the evidences, or you can again talk about the theory a bit more, that the theory said that you had the westward drift of the continents and the movement of the continents away from the poles, and this was based on the reasons and certain assumptions taken by Alfred Wagner. Now, his theory was given or supported by the various, you can list down the various evidences along with it as well. And in the case of evidence writing, when you're writing the evidences, make a bullet point, have an underline, write a couple of sentences, draw the diagrams. In all the geography answers, diagrams, very rough diagram, okay? Very rough diagrams and flow charts. are a must. You cannot have an answer of geography without either of these. So if there is a scope, always there is a scope to provide some or the other kind of a diagram, always. So provide a rough map, provide a rough sketch, any rough diagram. And here, please don't start beautifying your diagram, right? Please don't spend all of your time in forming a very beautiful diagram that may be printed in the book sometimes, because that is not your purpose. Your purpose is to convey the larger meaning here. Many of us, we make notes in the sense that eventually when all these notes are completed, then it should look so pretty, so clean, that if someone else reads it, they will also be mightily impressed, right? But those notes, you will find that after a couple of years, if you yourself go to your market, to the market, nearby market, you will find those notes being circulated in the market as Xerox copies. So please don't make notes for that commercial purpose. Anyways, you will not be paid anything for those circulation of notes, so you have no profit in that. Nobody even will come to know that which individual has prepared that notes. So always prepare notes in such a manner whereby you will always be able to revise that in a quick fashion, in a very short time period. Don't beautify it. And same is the case with answer writing as well. Don't over beautify it. Any diagram that you draw, you should have the ability to sketch the entire diagram within 30 to 45 seconds. At max, it should take you 1 minute. Any diagram, if it is taking you more than 1 minute of your time, it is too much. Because for every answer, please understand, right from the time of reading the question, understanding the requirement of the question, putting your pen to paper and finishing the entire thing, you have around 8 to 9 minutes for every question. So that is where efficiency counts. Okay. Now here, for example, in this particular question, what kind of diagrams can we draw? So here we can draw an image for, let's say, jigsaw fit. Jigsaw fit, a rough diagram can be indicated. Then, for example, what do we mean by placer deposits? They can be indicated. The entire postulation of Pangea being broken into two. Pangea being broken into two. All of these can be added. Now, here again, let me point out, many of the candidates, they have read so much books. They are so very knowledgeable. They have already reached that level of Zen feeling, for which you have to do all the various different types of things. Many of the candidates have already attained that. So in their answer writing, you will also experience as if you are reading some kind of a very textual book. So they will write the entire text, and at every place they will say diagram in the next page, diagram in the next page. Please don't do that. Just because it is convenient for you to draw all the diagrams at one place, please never replicate it in your answer copy. Wherever the requirement is, in the side, in the small corner, draw the diagram so that immediate visual impression is created. That is very much required. Now, also, another thing important is you have to write the requirement of the question. So, write about what is asked. And not what you know. Okay? So, here again, many of the times it happens that we look at the question and we do not, and sometimes we get so overwhelmed and so excited that I know so much about it that you want to fit everything that you know in that question itself. That is the approach. Now, that is an absolute wrong approach to take, because what it does is it ends up creating a wrong impression in the mind of the evaluator as well, that this person is filling in the pages unnecessarily, and the demand of the question is not understood. So what is the basic question which is asked? That needs to be understood very clearly and very carefully. And once you understand the basic question and its demand, stick to it. Don't deviate from it significantly. Okay. Now, after that, conclusion. Conclusion is of two types in the case of subject of geography. First of all, here, one of the conclusion will be if you have a technical kind of a question, a pure technical question, like the above one, like the question that we see here. If you have a pure technical question, a pure content-based question, so here you have to, in the conclusion, you have to write the summarization. Summarization of the entire answer. That is, what is the gist that you extract out of it? And then here also implications. For example, in this case, in the conclusion, you can write that the continental drift theory was rejected because of the faulty reasons cited by Alfred Wagner, but later on paved the way for the postulation of the developed plate tectonic theory. So here you, in that brief answer, you are in the brief conclusion, you are also talking about that how this continental drift theory is significantly helpful for the future as well. And then eventually, in certain problem-based questions, here, right way forward, and give a positive connotation. Always conclusion needs to have positive connotation. Always. Okay? So that is how you have to create the answers for geography. And whenever in doubt for any different question, whenever we will be discussing about the answer writing, etc. So this is basically how you will be able to write that answer. Refer to this page. This will be with you for perpetuity. So this page, revise it, look at it, whether you are fulfilling the criteria, and then you can carry out. Okay? Suggestions and way forward, they are similar, Sakshi. So that is to be written only in problem based questions. For example, let's say we are dealing with a question like water scarcity in India. Why is it that India suffers from water scarcity? So in the conclusion you can write that unless and until we carry out the solutions like water conservation, water harvesting, etc., there will always be a perpetual water scarcity, which can only be solved by collective participation of citizens. And this is how you can provide the suggestions as well. Okay. So that is about your answer writing. Since last week, many of you have written to me that you did not tell me about the answer writing and how to write an answer. So that is why that had to be addressed. Now moving ahead. So here we had seen earlier that the continental drift theory, that was not accepted, that was rejected. Now this was a theory which was rejected. This was earlier provided in the 1912 and 19 in that decade it developed. It was translated into English into 1920s. But here till that point of time you have to understand that 1900s has been an era of discovery. There has been a significant amount of greater discoveries which have happened during the 1900s. So it was during the 1900s where earthquakes started being studied in greater detail. Now, when you have an earthquake, when you receive or experience an earthquake in a region, now that earthquake also brings about the shaking of the earth's surface. But at the same time, the seismic waves give us an idea about what is present in the interior. It is by the study of these earthquakes that in the 1900s, our understanding of the interior of the planet, the structure of the planet, the layering of the planet, that started becoming much more clearer. We also got an understanding that in the central portion of the planet, in the innermost portion, the temperature is very high and temperature decreases as we come closer to the surface. It is by this that we got an understanding that the structure of the planet is very similar to that of a coconut, where the hardest part that we come across is basically the thinnest portion, and here that is the crustal layer. And the mantle, even though it is substantially thick, solid, dense, but it is a kind of a squishy thing, right? It is not completely as hard a solid as you see the rocks to be present here. It is something in the bottom layers of mantle, it can be compressed, it can be squeezed, it can expand ever so slightly. So that is present. In between the mantle, you also have the presence of asthenosphere. And then you have, in the case of coconut, we have the liquid inside in the center. Here also we have liquid core. However, there is one exception, that in the liquid core, we have a solid central part of the core as well, which is unable to melt because there is significant amount of pressure being applied from all sides. That is why the inner portion of the core ends up remaining in a kind of a solid state. Now, here, another now till now we had seen that for the different continents and oceans and the shape and the presence and the distribution of all of these, we had seen about the fact, we had talked about the fact that this has got the earlier it was provided by the theory was provided by F.B. Taylor, where F.B. Taylor talked about the fact that the continents can drift. That is it. And he did not postulate a significantly detailed theory about it. It was Alfred Wagner who talked about the drifting of the continents, movement of continents from one region to another. Now, after this, another development happened around 30 years later. That is after Second World War. And that is again something where one individual tried to explain that how the oceans in itself are expanding with the help of the seafloor spreading theory. And then later on came the plate tectonics. In the meanwhile, you had the convection current theory which was provided. Now, why are we studying these theories? If continental drift theory was rejected, if let's say seafloor spreading theory, or if let's say convection current theory, why are we studying this? We are studying all these theories because some learning from each of these theories that has finally led us to the plate tectonic theory, which is the relevant one. Okay, so there were some learnings taken from continental drift, some learning taken from here, some learning taken from seafloor spread, and that is what took us to the plate tectonic, which is the relevant theory. That is why one needs to be aware of all this. Now, convection current theory was provided by a very renowned physicist with the name Sir Arthur Holmes. Sir Arthur Holmes provided the detailed convection current theory. Now, this was based on the properties of convection. What do we understand by convection? Now, convection is a process of heat transfer. For those of us who are not aware, even though this is something which you would have studied in your class 6th, 7th, or 8th standard itself, but let's say we have forgotten that, as is the case with many of us. We choose to forget these things. So let's assume we don't know what is convection. So convection is a methodology of transfer of heat. How? So it is very simple. So here, let's suppose you have the presence of a container or a beaker or any utensil on which, let's say, you are heating the utensil, let's suppose. And this utensil You fill it with water. Most of us, in some time or at some point of the time or other, we would have boiled water, or if we are privileged enough to never have to boil water, at least we would have seen someone boil the water. And if we are those kinds of individuals who have not even seen somebody boiling water and the boiling water simply straight away reaches us, then it is high time in your life to look at the water to boil, how it boils. So here, let us assume we know how the water boils. Now, if you would have observed water boiling, now initially what happens? When you put a pan or a utensil filled with water on the stove, immediately what happens? Immediately you will observe. It is not as if immediately bubbles will be formed on the top and it will start boiling all of a sudden. No. Initially, you will have small bubbles formed at the base. Right? You would have observed this, that small bubbles, they start forming at the base of the utensil. Now, why are these bubbles formed at the base of the utensil? And what are these bubbles composed of? What is bubble? Whenever you have a bubble in a liquid, that means there's presence of a gas. Which gas is present here? What do you think? Let us see if we are mentally awake or not. Okay, good. Carbon. So if we are boiling water, we produce carbon in the process as well, is it? Okay. Only two of you have managed to give the correct answer. It will be water vapor, my dear friends. It will be water vapor. In water, if something is converted into gas, it will be water vapor. Where will you get carbon, and where will you get the separation of hydrogen and oxygen? It will be nothing but vapor, water vapor. Here, always think about it logically, that if this is water and okay, so let's suppose this is water. Let's come to the very basics of it. I never thought that this basics would also be required. When you heat it up, it forms water vapor, which is a gas. This is liquid. When you cool it down, what is formed? You have ice, which is solid. Any state of matter gets converted into gas, liquid, and solid, right? Any state of matter that we have. So when you will heat water, it will always produce water vapor. Water vapor is the gaseous form of H2O itself. H2O does not always mean it will be liquid. H2O can be solid as well. H2O can be gaseous as well. So here, when the bubbles initially are created, how are these bubbles created? Why are these bubbles created? I'm sure any of us who has not observed the boiling of the utensil in the kitchen, I'm sure there is no one like that. You would have observed or at least seen someone boiling water. So if not, if you have never observed this, do this today, that put a utensil, fill it with water, switch on the stove. You will initially find the presence of small bubbles at the bottom of the utensil, at the bottom of the pan. Now, how are these bubbles created there? That is because at the base of it, that is where immediate heat is being provided in this region. First of all, the base of the utensil is being heated. Now that base getting heated overall leads to the heating of the water, and water getting heated gets the water converted into water vapor. Now this water vapor is a gas. As compared to liquid and gas, we know that gas is always going to be lighter. So this water vapor will tend to rise up. It will tend to rise up. When this rises up, that is when you observe bubbling on the surface. In the meanwhile, here, the top portion will be slightly cooler as compared to the bottom portion. I hope we are aware of that. So the colder water will replace the vacancy created at the bottom, and that is how you have the entire transfer of heat which is achieved. Heat is basically circulated, heat is basically transferred in the process. So that is how you have the heat being circulated and transferred. This entire transfer of heat by movement of materials leads to, or is known as, convection. And the movement of the particles which help in dissipation and transfer of heat, that is the convection current or the convection circulation. This circulation that we observe, circulation of materials, is known as convection. Okay, I hope this portion is clear. I hope we are aware circulation of material is what is referred to as the convection current in general. Okay, that is where you have the circulation of materials which help in transfer of heat. Now, using this simple phenomena of physics, this basically is about transfer of heat. Now, this same phenomena was used by Arthur Holmes in order to indicate that how heat is transferred from the interior of the planet to the outside. Right? So this convection current theory talks about the transfer of residual heat from the interior around the region of the core to the exterior. So this explains the transfer of heat from the interior to the outside. Now, how does that happen? How is it that it can happen that heat from the inside will be transferred to the outside? So, with the help of the convection current. And where will you find that convection current to be in existence? So, he said that this convection current is basically residual heat which is present in the interior. Residual heat is transferred from the interior via the convection current in the mantle. So, for example, when we, let's say, talk about the surface, we talk about the region of the crust. Let's say we talk about the crust. We have the mantle, and then we have the core. Outer core, mantle, and we have the crust. Now here, the residual heat will be provided from which area? It will be provided from the region of outer core. So here, from the region of outer core, you have the provision of residual heat from different portions. It is not fixed that from point A only heat will be supplied. If you have a hot object, the heat can be supplied or emitted from any portion. So here you will have residual heat, which is given out. Now this residual heat, what it does is, immediately above it, the portion of the mantle starts to melt because of the heat. Now that molten portion of the mantle, here let's say, this is the portion of the mantle which has melted down. Now this molten portion of the mantle, it will be lighter in weight. Liquid is lighter as compared to solid. Gas is lighter as compared to liquid. I hope we are aware of this basic fact. So liquid is lighter as compared to the solid. So liquid will always try to rise up. So this molten portion of mantle, why is it molten? Because of the source of residual heat. Now this molten portion will have a contact with the portion directly above it. It will start melting the portion above it as well. So this portion will also experience a kind of a melting. And like this, the entire portion above that will have the movement of the liquid. And as the liquid is moving, it will start melting the regions above it. And that is how you will have the entire convection current in the portion of the mantle. That is how we will have the entire convection current present in the mantle, where the colder portions will replace the molten portions. They will get heated up, they will rise up, and that is how the entire convection current is achieved. This is the convection current in the mantle. Convection current in mantle. Okay, that is what you find in this scenario, in this particular situation, that there is a rise of a convection current which is found, which is present in the region of mantle. Now here, basically, Arthur Holmes was not a geographer. He was not a geologist. He was a physicist. And he can talk about the expansion, contraction, heat transfer, etc. That is his specialty. But what is the impact it will have on the surface? That was not talked about by Arthur Holmes. Later on, it was understood that with the help of this convection current, it is this convection current which is present in the mantle, which gives rise to various different movements on the surface and also gives rise to various different impacts. For example, sometimes we observe land mass gets uplifted, sometimes the land mass sinks below. And these are phenomena happening across the surface where sometimes, let's say, the land mass suddenly starts rising very slowly at a time, not like you see in the movies that tonight you went to sleep, tomorrow morning when you wake up, there is a mountain in front of you because of some heavenly intervention. That is not how it happens. It takes its own good time, around millions of years of time altogether, but land can rise up, land can sink down owing to the heat which is present in the interior. Now here you have, when we talk about the convection current has got two different sections. This is the vertical section. When we talk about the convection current, this is the vertical movement. In this particular portion, you observe the vertical movement. And then here you have the horizontal movement. Right? So you have the horizontal movement, you have the vertical movement. So here, when we talk about it, let's say the horizontal movement, the upward movement. Now, what do you think it will have the impact on the surface if there is heat coming from the interior straight away hitting the surface? What do you think will be the resultant? Either the surface can break and you will have molten materials rise through the surface in the form of volcanoes, or it can push the surface slightly upwards. So upward downward movement will also be experienced here, slight upward pushing. When we have horizontal movements, they will try to stretch and they will try to pull the lands apart. So this convection current, from this, all that you have to extract is that this convection current will have an impact on the surface as well. What kind of impact, how that impact pans out, everything we will study in detail today itself. Don't worry about it. But just understand that this convection current has got impacts the Earth's surface. Movement of the Earth's surface and so on. But mantle is solid below asthenosphere. Right, sir? It is solid. But the solid also is of various types. So mantle, while it is solid, don't think about the solid that you see in the rocks here on the surface. It is a kind, that is why I have been giving you the example of a coconut. Not because I am a fan of coconut, because it resembles that kind of a solid state. Now, in the coconut, observe the hardness of the surface and observe the middle portion, the fleshy part of it. The fleshy part is also solid. The outer harder surface is also solid. But then they are different. So here, when we talk about the mantle, think about it as a kind of a squeezed out solid, right? But here also, it is still solid. So how is convection possible? If that is your question, that how is convection still possible? Convection is possible here because the residual heat, it will melt the portion above. And that portion will try to rise up. Why? Because after getting molten out or after melting, now that portion becomes liquid. In that immediate vicinity here, let's say the portion of mantle has been heated, it gets converted into liquid. Now that liquid will try to rise up because it is lighter, it is hot. Now that liquid, it will heat up the region immediately above it, that will also melt because this residual heat is consistently being provided from one area. So that portion above it will also heat up. So there will be further movement. Now it is all a kind of a squeezed out or a squished solid in a way. A pulpy solid, if you can think about. Now that pulpy solid means that immediately as the liquid rises up, starts rising up, you will have the solids nearby which will fill out the space. Whereas this particular portion starts heating up the materials above, melting the materials, and rising up in the entire process. That is how, now if this portion comes in and fills out the gap here, it is a squishy solid. So the portion from surroundings will fill the vacancy created, let's say here, and that entire process will complete a convection current. Okay? Is that clear now, Santosh? Yes. Okay. Vishal, convection current in complete mantle or only in asthenosphere? In the complete mantle. And that was indicated by Arthur Holmes, because at the time of Arthur Holmes, the aspect of asthenosphere was not very well understood. In fact, the initiation of understanding of asthenosphere you will find in the research papers which started appearing in the early 1970s. That is where you find the mention of asthenosphere quite significantly. Before that, entire mantle was considered to be one uniform portion. Okay. But yes, Vishal, you have a convection current in the portion of asthenosphere as well. We will study that in the form of the various different types of mantle plumes. One of them is also in asthenosphere. Sakshi, inner core is also as solid as mantle, not like crust. Inner core is supposed to be very hardened, the hardest of the structure that we have across the entirety of the surface. And inner core is supposed to be much more harder as compared to the mantle as well. Okay, so that is where inner core is different. Okay, is there still more to research beneath the earth? Always, Utkarsh, always. So it is not the end of it. Every volcanic eruption which happens, every earthquake which occurs, it gives us immense amount of idea about what is lying in the interior. For example, in the month of January when you had an eruption in South Pacific, January 2022, when you had an eruption in South Pacific across the Tonga Islands, you had hundreds of people, thousands of people who camped around in Tonga and New Zealand to collect the portions of molten lava. And studies are being carried out. Few of the research papers have already been published about where that lava would have come from and what would have been the origin of it. So there are researches which indicate that this lava would have stayed for a long period of time in the region of the Gutenberg discontinuity and so on. So that is how a lot of understanding is still left, still desirable. So this is the aspect about the convection current theory. Is mantle responsible for convection current? No, it is basically the residual heat which is responsible for convection current. In this example, if you think about it, is the liquid water responsible for the convection current here? No, if you remove the heat, there will be no convection current. So always the source of heat is responsible for generation of a convection current. Okay? Now, after this, after the convection current theory, which was provided in the 1920s, now after that, for around a decade and a half, our understanding about the interior kept on increasing. It was during this time, while studying about an earthquake and the impact of an earthquake, studying the various different ways in which the seismic waves travel. It was during this time that laymen made a discovery that the inner portion of core would be solid. And that is why, if you recall, if at all you recall, the boundary region between the liquid outer core and the inner solid core, that is referred to as Lehman discontinuity. It is based on that particular factor. We will come to it more when we come to the portion of seismic waves. But here, after this, you had the Second World War. And whenever you have a condition of a war, the scientific and technological advancements, they outpace anything else. There is so much amount of research development which happens. Now, during Second World War, most of you would have studied or you would have had better understanding of Second World War as compared to me. But I hope you are aware that during Second World War, Germany unleashed a new kind of weapon which was unknown to man by that point of time, which could target the ships and the various naval ships, the troop carrying ships, the resupply ships, which of the allied forces which were moving across the Atlantic, across the northern part, across the Mediterranean, they would be targeted by this new weapon developed by Germany. What was this new weapon? It was the U-boats, what today we refer to as submarines. Now, submarines during those point of time, they were the newest technology to be used in Second World War. And you had these German U-boats, which could stay underwater, come up to refuel, and come up to attack. They would attack and again hide underneath water. Now, the forces of United States, Japan, United States, UK or England, and France, they wanted an end to it because this was causing massive damages and unexpected damages. Unexpected damages hurt you a lot. When you have an expectation that there can be a kind of a damage due to this XYZ, you are prepared for it. But unexpected damage, it pinches you, hurts you for a very, very long period of time. So that is where they wanted an end to it. So they started working on technological advancements. And they came upon a particular instrument, a particular technology, which would help them look at what is lying underwater. And that was the detection or the development of the modern day sonar equipments, underwater radar of sorts, which would emit sound waves. What it would do is basically those particular equipments, if you think about it, those would be somewhat, let's suppose this is water, right? This is the base. Now here, if let's suppose you have an enemy submarine present in this region, right? Now, if the ship is moving here, If this is your ship, here you have the sonar equipment which would emit sound waves. These sound waves would hit a surface, and after hitting the surface, they would be reflected back. Now, by studying the reflection, you get an idea about the cross section, the dimension of the object which lies underneath. This was a major advancement. Now, by this, the German submarines could easily be plotted out. And suddenly, the forces of US, Britain, they had a kind of an advantage over Germany. They could detect these submarines now. They could hunt these submarines very easily now. But then, in 1945 marked the end of Second World War. Now, when the Second World War ended, it is not as if all these weaponries also were put out of circulation. These weaponries were in existence, these modern technologies were in existence. So that is when this particular technology of studying what is present underwater, this was utilized by various different expeditioners, various different explorers. One such explorer was the United States, or present in United States Navy, the naval expeditioner with the name of Harry Hess. Harry Hess was one of the expeditioners, one of these naval officers in United States. Now war had ended. Now what would you do with all these equipments? That is when, even during the war, when people started using these, they found a kind of a surprise lying underneath the oceans. Because up till the period of war, and till that period of time, in the early 1940s, the general understanding that mankind had was, look, the ocean surface appears to be plain and smooth. That means the ocean bottom would also be very plain and smooth. We did not even know the depth of ocean bottom in many of these areas. But our expectation was that the ocean bottom would be smooth. It was during Second World War where you had this instrument being used. That is when the realities in many places, they unfolded, in the sense that people came to understand that you had underwater mountains as well, underwater ridges as well, right? You had the kind of underwater ridges in a way. All of these were present. You had the presence of guyats. All these different structures were present underwater. Now, that immediately triggered the kind of curiosity that we need to study what lies underwater. And that is when Harry Hess started studying what lied underwater, especially in the case of Atlantic and in the eastern coastal or in the eastern part of Pacific, near the California coastline. He started studying that. And based upon the study, he observed something very unique. He observed the fact that under the oceans, you have the presence of very elongated and very large ridges. Ridge portions are very large. So you had underwater ridges. Underwater ridges. Now he found out that these underwater ridges, these are centers of volcanic activity. Here you have active volcanism which happens kilometers, hundreds of meters, or thousands of meters below the sea surface. You have volcanic eruptions which happen. Volcanic eruption happens here. So these were regions of active volcanism. This puzzled him that, first of all, when we think about fire, Nowhere in our imagination can we think that fire can exist underwater as well. Nowhere. When we think about volcanic eruption, always we think that it would occur on land only. How is it that volcanic eruption can happen underwater? So that was the first puzzling evidence that he came across. Now, that is where when he found out that this was an underwater eruption across these ridges, and these ridges were found to be in the middle of the oceanic areas. And that is why these underwater ridges, he also referred to it, or it was also referred to as mid-oceanic ridges in general. Now he started collecting sediment samples, rock samples from the nearby region. And there also something new came into existence. So rock samples and sediment samples from the nearby regions, they indicated a particular reality and a particular fact. Now, rock samples and the sediment samples, they indicated the fact that rocks and sediments closer to the ridges are younger, whereas younger in terms of age. And when we say a rock is young or when we say a rock is old, basically we try to end up having a postulation about how it is formed or when it is formed. Something which is old means formed much earlier. So here, rocks and sediments away from the ridges are older. Now, this is something that he found. Harry has found this underwater. Now, he also started looking at the sediments and the deposits at the ocean bottom, and something else puzzled him. When we talk about the various different rocks, I hope we are aware that we are able to calculate the age of the rocks. I hope we are aware of that. How do we calculate the age of the rocks? Or are we aware that age of the rocks can be calculated? How do we get to know about the age of the rocks? Okay. Good. It is carbon dating, right? C14. Yes, good. It is by the aspect of carbon dating where we are able to calculate what is the age of the rocks. Now here, when he calculated the age of the rocks on the ocean bottom, he was puzzled by the fact that while the age of the rocks on continents sometimes indicate that the rock has been formed 2 billion years back, 1 billion year back, even in certain cases, there have been evidences of rock formations on the continents which are as old as even 3 billion years. But when he started studying the ocean bottom, he found out that none of the rocks at the ocean bottom, they were older than 200 million years. So he found out the fact that while continental rocks are billions of years old, oceanic rocks are not older than 200 million years. This basically was the study that he carried out in the Atlantic. Atlantic Ocean. That is where he carried out the study, and that is where he came across this kind of a finding. Now, what does that indicate? When you see that oceanic rocks are young and the continental rocks are very, very old, that means what? That means these have been created recently. That means Atlantic Ocean has been created recently. That means 200 million years ago, there was no Atlantic Ocean in existence. And Atlantic Ocean has been created only 200 to 50 million years back. How has the Atlantic Ocean been created? So how is crust created? By the solidification of lava, by the solidification of the molten materials. They form these crustal layers and the crustal rocks. So based upon this entire aspect of findings that he carried out, he gave a theory, he propounded a theory, which is referred to as seafloor spreading theory. Seafloor spreading theory. Now, what is the postulation of this theory? Or what does this theory talk about? So, as per this theory, while the continental lands, since they have been formed, they are present as they are, the oceanic floor that gets created freshly, and also it has to be destroyed. Otherwise, you cannot have newer creating oceanic crust and endless creation of oceanic crust. So he said, as per this theory, he said that continental land masses have been created earlier as compared to the present day oceanic regions, and the oceanic floor keeps on getting created and destroyed. Consequently and significantly regularly, it is created and then destroyed again. Now, that is what leads to a kind of a circulation. That is why you have the conditions of the ocean floor, which is significantly younger. So that was the basic postulation. How is it that the oceanic floor is created? How is it destroyed? What did he say about that? That is something we'll take a look into. So that is the aspect about the seafloor spreading theory. Now, this seafloor spreading theory basically was provided by Harry Hess. Harry Hess. Okay. Now, he said that look, the oceanic floor that you see, this oceanic floor gets created at these ridges, underwater ridges, which are a source of volcanic eruption. So he said, oceanic floor is created at the mid-oceanic ridges, the underwater ridges where you have volcanic eruption. Mid-oceanic ridges. Now, I hope we are aware that underwater, you also have the presence of trenches, right? Trenches, what are trenches? Trenches are those portions where suddenly the depth increases. It is a kind of, if you think about, let's say this is the water body, let's suppose. Here you will have a kind of a deeper portion, generally at the continent-ocean boundary, that is where you will come across these deep portions. The deepest trench in the world is what? It is the Mariana Trench or the Challenger Deep, which is situated in the portion of the Western Pacific, having a depth of close to around 8 to or around 11 kilometers from the sea surface, roughly. So that is a trench. Now, here, most of the trenches you will find, this is a trench. So most of the trenches you'll find to be present where? At the continent ocean boundary region. So I said that the older oceanic floor, or before this, newly created, because by volcanic eruption you will have new creation of the crust. That is what he's talking about. So newly created crust pushes the existing crustal regions to the sides, right? And then the older oceanic crust is consumed at the oceanic trenches. So this was his theory that he propounded. Now, when you have a newly created crust, that pushes the existing crust to the sides. So he said that, look, a crust is created at this volcanic portion. A volcanic eruption has happened, which has created a newer crust. So that means the existing layer would be pushed slightly to the side. Again, a new eruption will happen. Again, more crust will be formed. The existing one will push to the side. So that is how the entire process will unfold, where the newly created crust will push the existing portions to the side. And that is how you have the sea floor, which is spreading. So in this portion, this particular event leads to the expansion of the sea floor. Leads to the expansion of the seafloor. And by this, he could explain why North America and South America, they are moving away from Europe and Africa respectively. Because the Atlantic Ocean in itself has been created around 200 million years back to 20 million years back. The entire Atlantic has been created. So by this, he could explain the aspect of spreading or expansion of the sea floor. So look at the observations that he made first of all. So oceans are not featureless plains. It consists of mid-oceanic ridges, rise, various different aspects, trenches, plains, seamounts, etc. Oceanic rock sample in age were nowhere more than 200 million years old, whereas continental rocks are way older, in certain areas even 3.2 billion years old. That is something that you find in the case of continents. That means obviously the continental rocks or the continental crust is unable to be recycled, whereas the oceanic crust is consistently being recycled. That is why the oceanic floor is newer in terms of age. Now, near the mid-oceanic ridges, rock samples were younger, and near the trenches, as you move at the ocean continent boundary region where you will find the trenches, the rocks are the oldest. But there also, the age is less than 200 million years. Now, on the crest of the mid-oceanic ridges, crest means the top. Crest refers to top. So on the top of these mid-oceanic ridges, cracks with the continuous active volcanic eruption. So these were volcanically active. You had volcanic eruptions and eruption of newer magma and newer lava which was happening. Age of rocks and types may be similar for any two places. For example, what this indicated is, let's suppose you have a kind of a mid-oceanic ridge here underwater, let's suppose. Now he said that if you move equidistant away from this mid-oceanic ridge, the age is similar. Okay. If you are moving equidistant away from these ridges, the age is significantly similar. So that is the observation that he made, the observation that he carried out. Now, this is something which he pointed out. So a broader understanding of what he wanted to convey was very simple, that look, if we have this as a continent, this again as a kind of a continent, and here you have the presence of water body. Underneath the water body, here let's suppose you have the presence of a trench. Let's suppose. And this is your mid-oceanic ridge. Mid-oceanic ridge. Now, what he said was that here you have the volcanic eruptions which are happening, that is pushing the existing crust aside, and over a period of time, this crust is moving. Obviously, the rate of formation of newer crust and the rate of consumption of the older crust cannot be the same, due to which you have the entire sea floor in itself which is spreading, which is expanding, due to which the different areas are pushed away. And these are your oceanic trenches. So it is here that the older crust is getting consumed and the newer crust is getting created here, and the older crust is consumed in that particular portion. That is what he said. Now, how is it that the newer crust is getting created? Newer crust, ideally, from the volcanic eruption, how is it that you have the newer crust which is pushing aside the older crust? Let us understand the principle behind that. So, for example, let's suppose we consider the ocean floor. Let's suppose here you have the mid-oceanic ridges. Okay. Now, mid-oceanic ridges, point of active volcanism. So here there is a crack which develops. So you have significant amount of volcanic activity which happens. Now, over a period of time, there will be creation of a newer crust here in this particular portion. A gap has opened up. That is when the volcanic materials will come up. Let's say this is the newer crust which has been created. After some time, how will this appear to look like? So while the newer crust is getting formed there, it will basically push the existing ones to the side. It will deposit on top of each other as well. That is how ridges are formed. That is how the ridges gain some amount of height as well, because the volcanic materials, they will deposit on top of each other as well. But also understand the very simple dynamics here. Very simple portion of physics and very simple portion of logic rather, because when I say physics, immediately few people will switch off their mind that this is complicated concept, not for me. So here, think about it in a logical standpoint. If you have a portion like this, now if I start applying the weight here, I significantly start applying weight. So here this portion will be compressed. And when this portion is compressed, this will spread out like this. If you have a paper has got a fold, and if you put pressure on the fold, what will happen if there is a fold like that? If I keep on exerting significant amount of pressure, what will it result into? It will eventually flatten it out. It will eventually push the existing one, so there is a spread happening. So that is why, while there will be accumulation on top as well, it will exert a pressure which will provide that extension. After some time, the volcanic eruption will keep on happening. That means the heat is being provided there. After some time, again, the rock will crack open due to the heat. The heat which is provided, that will again open up the rock. Now, this time, the portion which was created earlier, that portion will also be divided into two. Observe this portion which was created. This will also break open. This will also crack. Again, you will have heat which is provided. Right? So again, you will observe the formation of newer crust here. Newer crust will be created here by solidification. Again, that heat will be provided, leading to another development of crack here. So after some time, again, you will observe that a crack has opened up across both sides. A crack has opened up. Now, this would mean what? That the older one is here. The one created more recently will occupy the space here. And then you will have the scope for a newer one. So this is where new solidification will be observed. So that is where you will observe that you have frequent creation of newer rocks and newer crust. So that is how, because of the heat provided from the interior, newer crust is created, pushing aside the existing crustal layers and pushing the crustal layers to the sides. So that is how you have creation of a newer crust, and expansion of existing crust. Existing crustal layer. So the entire process, if I have to recap, there is heat provided here. Observe there is heat provided in this portion. Now this is your mid-oceanic ridge, right? This is the portion which is your mid-oceanic ridge. Now this portion of mid-oceanic ridge means you have volcanic eruptions happening in this area, which will spill out. So this will solidify here itself. Now once it solidifies, let's say a newer crust has solidified here. But again, after prolonged heating from the interior portions, this particular area which has solidified, this will start developing some cracks here. Some cracks will develop here, right? And the some cracks will develop means more materials will be pushed up. More materials will be pushed up means the existing materials will be slightly pushed aside. Those materials will solidify. Then again, more materials being pushed up. So this cycle is repeated, and that is how newer crust is created at the ocean bottom, leading to the seafloor spreading. This was postulated by Harry Hess. Now, this theory basically concentrated on the creation of the newer crust at the mid-oceanic ridges. This is a map, physical map of the world, indicating the various mid-oceanic ridges that you have. Various different mid-oceanic ridges that we have. Now here, if you will observe, you have various different mid-oceanic ridges All this, which are indicated by light blue, all these are your ridges. Right? All of these are basically your ridges. And these are continuous in a way. They stretch across the entirety of the planet, almost. Overall, these appear to be like small mountains or small hills underwater, because volcanic eruption will also lead to accumulation on top of each other. It is here that the ocean is expanding. The ocean is expanding here. Okay? It is across this region why you have these ridges where you have a motion like this. Okay? So that is basically the mid-oceanic ridges which he concentrated upon. But his theory of seafloor spreading also had drawbacks and limitations. For example, his theory does not explain that how the sea mounts, the various different features that you come across in the ocean floor, how they have come into existence. His theory does not talk about it. It does not talk about the movement of continents at all. It only talks about the movement and circulation of the oceans. It does not speak in terms of lithospheric region, that only the crust is being formed, or is there any other formation which happens. Also, as per his theory, there is a recirculation which is happening. So every ocean where you have a mid-oceanic ridge, at the continent ocean boundary, it should have an oceanic trench. But that is not the case. It is not the case that at every ocean continent boundary, you will have the presence of an oceanic trench. So that again defies the normal logic. So there were limitations to it as well. But as this theory was basically talked about, and as this theory came into prominence in the early 1950s, around 1953, by that point of time, obviously, you had greater research which was carried out. And later on, by studying the magnetic property, another aspect of this theory which he talked about, and that aspect of the theory is age of the rocks are similar when you are equidistant away from the rocks. Now, this particular point or observation was highlighted by the other different physicists and geologists, and they explained this particular mechanism with the help of paleomagnetism. We'll come to it. So, this seafloor spreading observed by Harry Hess, a quick recap, now corroborated the fact that continents indeed they do drift, and it formed the basis of plate tectonic theory here. Now, here you also had later on people trying to prove the observations of Harry Hess through a mechanism, through a methodology that we refer to as paleomagnetism. What is this paleomagnetism? Paleo is something which is old. Anything which is old is paleo. Paleomagnetism is the study or the calculation of the age of the rocks by studying and inferring the magnetic properties of the individual atoms and the individual particles. So here it is the study of age of the rocks by studying the ancient or the older magnetic alignment of the particles in the rock. What do we mean by this? What is the meaning of the fact that you study the age of the rock by studying the older magnetic alignment? Let us simplify this. So we do know, we have studied about the aspect of geomagnetism. Geomagnetism means We have looked at the fact that planet Earth has got a magnetic field associated, right? So it has got a kind of a magnetic field which is associated here. Magnetic field lines come to the north, move to the south, and here that is how the magnetic field lines behave. And these magnetic field lines will have a kind of an alignment as well. Now, let me ask you a basic question that we discussed last week. This magnetic field line, which is generated by Earth, this magnetic field line, will it be consistent or is it something which can change? What do you think? Magnetic field lines. Very good. It changes. It can change very, very frequently. Okay? Keep that in mind as we move ahead, that magnetic field lines can change very frequently. Now, when the newer rocks are created, how are the newer rocks created? By solidification of molten materials. That is how newer rocks are created. After that, that rock can get converted into different types. That is a different matter altogether. But newer rocks are created how? By solidification of molten materials. Now, when a molten material is solidifying, it will have the particles which will experience the magnetic field. Let's suppose here you have a rock piece which is solidifying. Now, the particles which are present here, they will experience that magnetic field. They will align themselves before solidifying. Ever so slowly, they will align themselves in that magnetic field of action. Whatever iron, etc., other metallic minerals which are present, they will be influenced by the magnetic field of the planet Earth. If you have a small compass attached to your watch, you will observe that it always aligns itself in the north to south direction, depending upon the magnetic field of the planet. So that is where, as the rocks begin to solidify, the particles will also align themselves in the direction of the magnetic field always. So here, let's say they have aligned themselves in this direction. Now, after some time, after let's say 10 years, 20 years, the magnetic field, let's say, has reversed. Let's assume the magnetic field has reversed completely. But by this time, the rock has already solidified. The particle has already solidified along with that alignment. Now, let's say after 20 years, 30 years, the magnetic field reverses. And then a newer rock is being formed here. Let's suppose a newer rock is being formed here. And the alignment has now been reversed in the past 30 years. So that means this will indicate an alignment like this as it solidifies. Now, by studying these rocks later on, if we have an idea that what the magnetic field of the planet would have been 500 million years ago, 490 million years ago, 400 million years ago, 200 million years ago, let's say we have a chart, we have an idea about the magnetic anomalies that the Earth has gone through. Now, by studying the rocks and the direction of the magnetic field alignment, we can match it up with the chart. And by that, we can calculate the age of the rocks as well. So this study is paleomagnetism, where you are studying the magnetic property of the rock particles, and by that, you are actually matching it up with the age, the magnetic alignments and anomalies of the planet Earth, and accordingly, you are able to calculate the age of the rock structure. So paleomagnetism is used to study the age of the rocks. Now, Harry Hess had given a kind of an observation that, look, when you are closer to the mid-oceanic ridges, the age of the rocks are younger, and as you move slightly away, the age gets older. And equidistant from the ridge on both sides, the age is similar. Again, equidistant, the age is similar. So this particular observation was further cemented by the study, the evidences collected by paleomagnetism. What was it? So it talked about the fact that, let's suppose Let's suppose here, this is the kind of a rock. Let's suppose. Now here, what was indicated was that as you move away from the mid-oceanic ridge, the age is similar. Let's suppose the central portion is what indicates the mid-oceanic ridge here. Let's assume this indicates your mid-oceanic ridge. Oceanic ridge. And basically, on both sides of the mid-oceanic ridge, the study was carried out to indicate the age, to calculate the age with the help of paleomagnetism. With the help of paleomagnetism, that study was carried out. Initially, to calculate the age, what was done, to give you an idea that in the initial period, obviously nobody will have the mindset that let me start collecting the samples from both sides of the mid-oceanic ridge. If let's say you have been given money, someone has given you a grant that go and find out the age of the rock and a pattern or a trend in the age of the rock, you will never go across both sides of the ridge. You will start from one side of the ridge, come to the coastline. That this is what is the pattern of the age. Later on, while this was matched with the other side, that is when that eureka moment struck that the age is very similar. How? It was observed that the magnetic patterns indicated here and here, they are very, very similar, indicating that they would have originated at the same point of time. Then the magnetic patterns indicated here and the magnetic alignment indicated by the particles here, that also were very similar, indicating again they were formed at the same time. Then the magnetic patterns indicated here and the ones indicated here, they also indicated that it was formed at the same point of time. So here basically what it indicated was that you have the rocks of the same age. Okay, so as you move away from mid-oceanic ridges, equidistant from the mid-oceanic ridges, you come across the rocks which have the same age, which tells you what? Which tells you that it is at the center where here newer rocks are created. Rocks are created. And then they are pushed aside. Slowly and steadily, they are pushed aside. And that is how the older rocks, they are far away from mid-oceanic ridge as compared to the one very close to mid-oceanic ridge. This was indicated by paleomagnetism. Now, many of the people and many of the textbooks you will find that they attribute Harry Hess with the study of paleomagnetism also. That is not the case. While Harry Hess was able to calculate the age of the rocks and on one side of the ridge, he did not substantiate his study with the help of paleomagnetism. So it was done almost 10 years in the late 50s and in early 60s. So by that point of time, Harry Hess was not active anymore. So by that point of time, that is when this was substantiated by other geographers and geologists who carried out the research of paleomagnetism, and they corroborated what Harry Hess had propounded earlier. Now, earlier, people did not trust what Harry Hess had said because they were not very sure about the observations that he made. That this is a naval expeditioner, what are the various different observations that he has made? They did not trust him very much. When the aspect of paleomagnetism was used to indicate that what he was saying was correct, that is when people started working on this theory. That is when they started finding evidences based upon the earthquakes and the various different earthquake and volcanic eruptions which happen across the world. That is where they started concentrating upon it, and that is when eventually we had the arrival of, or the postulation of, plate tectonics. So here when we talk about the sea floor, so it was the first comprehensive theory to talk about the movement and formation of sea floors. And simultaneously, other scholars such as Mackenzie, Parker, and Morgan in the 1960s, not 1960, actually it is 1967. So in the 1960s, developed a more comprehensive understanding of the movement of the different parts of the Earth crust and the related formation. And that particular aspect developed by Mackenzie, Parker, Morgan, Wilson, Tuzo Wilson was also very important for this. And that is what encapsulated and postulated the theory of plate tectonics. Now, when we talk about the theory of plate tectonics, it basically talks about the very simple principle that the entire lithosphere is broken into plates, and these plates, they tend to move over the molten portion of mantle. Which portion of mantle are we talking about here? Which particular portion? Asthenosphere. Asthenosphere. Okay, so the lithosphere is broken into plates, and these plates, they move over the mantle. Now, what is lithosphere comprised of? It is comprised of the crust plus solid upper mantle. Okay, and then these plates, they move with respect to each other, relative to each other, and that is what has given rise to the present day moving continents and oceans. So this confirms what Alfred Wagner had said around 50 years back, but then the reasoning is completely different. We'll talk about the reasoning of it all, but before that, we'll take a break because I can see for many of us. So, how many of us have not understood anything till now? Be very frank. I'll not take your names. So, for how many of you it has been like a bouncer which has consistently moved up, and you are simply waiting that when is the break time? I had ordered this for lunch and so on. Please feel frank and let me know. Okay. Okay. No issues. Fair enough. See, even if everything is bouncing, so it is very, very difficult to understand, to basically reflect on that. Uh, I'll do one thing. I'll give you 10 minutes of time. Think about those 10 minutes. During those 10 minutes, that what is the issue that you have not understood, and then we'll come back at the break. We'll give another 5-7 minutes to solving those issues or the problems. Okay. Yes, Komal. Paleomagnetism supports the seafloor spreading. Didn't understand the part of paleomagnetism. Okay. Okay. So here, basically, I will put it up at the portion of paleomagnetism. Try to reflect upon it. We'll take a 10 minutes break and then we will be back. Break for 10 minutes. 10 minutes should work for you. I hope 10 minutes is fine to splash water on your face, to do whatever you want, and be back in 10 minutes, and then we continue. Okay. A confirmation for the audio, please. If the audio is clear enough, kindly confirm. Thank you. Sai, we are going very, very slow. So, see, understand, I can stress upon a particular topic even in greater detail if you want. You need to be, but what I want from you guys as well is the ability to pinpoint the portion that you have not understood. It cannot be that entire portion is a kind of a blur, that I don't know what has happened and then repeat the entire thing. That won't be done. If you are able to pinpoint that, for example, let's say paleomagnetism is something that you have not understood. So that is something which is easier to re-explain, easier to come back upon. So always have that kind of a stress. In order to study, also keep that in mind, that whenever you study something, it is never going to be the case that the entire subject is not understood. Go to the root cause, which portion of that subject, which portion of that particular chapter, which particular portion of a topic is not understood. When you pinpoint that, finding solutions becomes much more easier. Okay. And Vishal, why the mid-oceanic ridges formed at a specific location? Is it because of non-uniform distribution of material and non-uniform residual heat over the outer core? Absolutely, yes. Very good. So it is basically, Vishal, because of that phenomena itself, that this residual heat, it is not as if it will be given out only from one particular region. So newer mid-oceanic ridges can always come into existence. And the older ones, they can never, or they will never experience volcanic eruption again. So depending upon where that residual heat is being released. And that residual heat, when it is released from a region, it can last for many years, many hundreds, thousands, and even millions of years altogether. For example, the mid-oceanic ridge underneath the Atlantic, which has led to the formation of Atlantic Ocean, that has been in existence for over 200 million years. And it will continue to exist for many million years more. The mid-oceanic ridge underneath the Indian Ocean, which is leading to the movement of Indian continental landmass, and the Indian landmass being pushed over to Eurasia. So that again is basically because of the residual heat being released there, and it will continue to happen for a much longer duration as well. Okay. So, Jay, when we talk about C14, C14 is used, it is an isotope of carbon for carbon dating. Paleomagnetism, here also you get an idea about the age of the rocks, but not by carbon dating, by looking at the magnetic properties of the particles which are present in the rock. The rock is composed of various different particles. Those particles would have solidified at the time of formation. At the time of formation, when they would have solidified, they would have aligned themselves significantly in a particular direction. So that is what gives rise to the calculation of age of the rocks. Okay, I hope that is clear, Jay. And Sakshi, the Arthur Holmes theory. Okay, so the convection current theory, the third and the fourth point you are saying. So there is no point-wise allocation of this. But nonetheless, let me tell you just the brief about the convection current. The convection current theory talks about the release of that residual heat from the interior in the portion of the outer core to the extremity in the portion of the crust. And how is it that heat is transferred? By the convection current. Where do you get that source of convection current? From the heat provided from the outer core. That is what generates the convection current, and that is what pushes, or in a way gives rise to various different land activities that we see around. We'll come across the various different events and eventualities which happen on the surface due to this convection current. We'll come to it when we study about the plate tectonics, but this is what the convection current theory is. Okay, can we proceed further now, or any issue which is not understood? Please feel free to point out. Okay. So now we come to the plate tectonic theory. Now, how is it that we get to an understanding, or that we get to a conclusion that lithosphere is broken into various different subparts or the plates. How did we come upon this particular understanding? How is it that people finalized this particular portion, that it is divided into plates? We started observing the various different earthquakes and the various seismic events and volcanic eruptions which were happening. It was found out that all these basic earthquakes which keep on happening, the seismic events which keep on happening, they are restricted to a particular portion only. They have a set pattern. It is not as if randomly today morning an earthquake will occur in Odisha. No. Even in India, when you have earthquakes, you would have observed that occurs largely across the northern portion, the Himalayan region, or in the portion of Gujarat. These are the centers of earthquake. Then otherwise you will come across the fact that earthquakes, they do occur all around the region of the Pacific in the world, across the region of Mediterranean. So by studying all these, we finalize the various different plate boundaries. These are the various different plates across the entirety of the planet. Here you will find that the plates, basically depending upon their size, they are classified into major plates and minor plates. Major plates, the larger ones, the substantial ones. And you have the minor plates which are very, very small. Now, these plates, in most of the cases, you'll find that, for example, if you talk about the major plates, which are the major plates? The larger ones. So you have the Eurasian plate, we also have African plate, then we have the North American plate, then we have the South American plate, then we have the Pacific plate, and we also have the Antarctic plate. Along with that, we have another major plate, which is the Indo-Australian plate. Australian plate. So in total, we have 7 major plates as of now. But in the near future, this is not going to be the same, because as we speak, the Indo-Australian plate in itself is getting divided. It is being broken into two. So let's say few years from now, in the sense that few thousand years from now or few million years from now, we will have a separate Indian plate, and we can also have a separate Australian plate. But as of now, these are your 7 major plates. Now, one feature that you will find across all these plates is that they will consist of both oceanic as well as continental crust. Other than the Pacific plate, all the major plates that you will see, they consist of both oceanic and continental plate. Okay? They consist of both of them. Now, obviously, the interactions that they will lead to, that will also create significant amount of various landforms and various events. And how do we get to know what is the plate boundary? By studying the earthquakes and the volcanic eruption zones. So the plate boundary, when you come across, the plate boundary is determined by the zones or the study of earthquake zones and volcanic activities. Okay. Now, let us understand what this theory talks about and what this plate tectonic theory is. So basically, this tells you about the fact that the plates, they do move with respect to each other. The entirety of lithosphere is divided into plates and they move with respect to each other. But why do they move? What is the reason why the plates, they do move? So here, for example, when we talk about it, let's say, which slide you want me to indicate? The list of the major plates will be given to you. Don't worry about it. I have a separate slide in which this list is also given. So don't worry about noting it all down. Okay. So I hope that is understood. So here, again, take the help of a simple experiment that you can conduct at your house itself. Let's suppose you take the same utensil in which you had boiled water. Let's take the same utensil. Now here, you have filled it with water and on top of it, you have kept two floating blocks of wood, A and B. Let's say you have kept two floating blocks of wood. And this is heated up. Now, observe this. In the initial portion, if you have not observed this particular phenomena before, you can do it at your own house. You can practice it. Instead of wood, you can keep thermocol or anything. Ensure that in the initial stages, before the heating has been provided, they are together. When the water is calm, place them together very close to each other. Now, after that, you provide that kind of heating. When you provide that heating, basically, after some time, you will observe a unique phenomena where A and B, they start moving away from each other. And why do you think that happens? That is because the bubbles, they will be rising up and there will be a kind of a convection current initiated in that liquid water. So that convection current is pushing A and B aside. Now, the same phenomena is at place here also, where the plates, the movement is initiated due to the convection current. Now, where is it that the convection current is present? That was provided by Arthur Holmes. Convection current is present in the mantle. And why is the convection current in existence? Because of the heat provided from the outer core. Where does the outer core get its heat? From the residual heat which is trapped since the time of its formation. So let's suppose we have a situation where we consider one plate boundary here, a plate boundary. Now let's suppose here you have the mantle and here you have the outer core. So there is a kind of a convection current which is initiated in the portion of the mantle due to the provision of the residual heat, due to which these plates, they will move aside. The horizontal component of the convection current, is something which will basically provide that kind of a push. Okay. Now, here, when we talk about it, Suppose the heating would be underneath the right side of block B. Okay, I will come to it. Utkarsh, don't worry. And Jafrina, mantle will pull a current or magnetic field. Mantle will not have the kind of a magnetic field pull. Magnetic field is exerted by the movement of the outer core. The mantle will have the heat transfer, the residual heat which is trapped. Observe this, try to imagine it. Suppose this is the planet, this is the region of mantle or the crust overall, let's suppose. And here you have the core, right? Let's suppose. Now it is from this portion of core where periodically residual heat is provided from different places, periodically. Now when that residual heat is provided, it gives rise to a kind of a convection current here. It will give rise to a convection current here also. It can give rise to a convection current here also, here also. So like that, multiple different convection currents are in existence in the portion of the mantle. So this is basically the convection current. So multiple different convection currents are in existence in the portion of mantle. And it is totally dependent on the residual heat which is supplied. This residual heat, it might be possible that here in this place, residual heat then suddenly ceases to be in existence. So no convection current will be provided there. Or let's say a new portion of residual heat is being given out of here. So a new convection current will come into existence. So it is defined by the emission of residual heat. Now, here you might have a question, as has been pointed out by one of you. Here you might have a simple question that this convection current, will it always occur only at the plate boundary? It can even exist somewhere else, and it can also come into existence underneath an existing plate. What happens when you have an existing plate, a larger plate, and a convection current is initiated here? Heat is rising up and a convection current is created here. Now, in that situation, what will happen? Here you don't have a plate boundary. So in this case, I would take you back to your childhood days if you have played with a plastic scale or a plastic ruler. Now, oftentimes when you get that power that, let's say, you have the candle to yourself or a flame to yourself, you try to melt various things. You try to see that when the things will melt, etc. So let's suppose if ever you have tried to melt a plastic scale. Now what happens? When you provide that heat, let's suppose this is a plastic scale that you have, and you keep it over a flame. Let's suppose. Now what happens? Does it immediately melt? No. Does it immediately break? No. In the middle portion, it will start thinning out. It will thin out due to heat. It will start becoming thinner and thinner. If you pull it, it becomes much more thinner. Continue to pull it over a period of time, eventually it will break, isn't it? A very similar characteristic is indicated by the lithosphere as well. When you have that provision of heat, initially what will happen in this area, first of all, it will start to thin out here. It will start becoming thinner and thinner. Now, it is not directly the flame of a candle that is concentrated in one region only. It is an entire convection current which is present. So when you have the convection current, the horizontal portion of the convection current that will create the pull. The horizontal component of that convection current will try to tear away or try to pull the landmass. What you were doing with your hands in the case of the plastic scale, now that activity will be done by the convection current, the horizontal movement of the convection current itself. Now, in this situation, what will happen? The central portion, it will continue to get much more thinner because now it is pulled on both sides as well. So it will continue to get much more thinner. Now here, I want you to observe the top surface. The top surface, basically you would observe, has got thinner in the sense that there's a kind of a depression created in the name of getting thinner. And as you pull it up, the material gets thinner. So what happens here? A kind of a very deep depression is created. Now, can there be a possibility that nearby water bodies of the oceans, they will enter this region? Can you think about a possibility like that? That the nearby water bodies which are present, the various different oceans are present. So in that nearby water body region, the water body will enter that area because now there's a creation of a depression, isn't it? So that is what happens. Here, generally you will find as the land is being pushed or pulled away, it is filled with water, not the groundwater, etc. The nearby oceanic water enters into this region. So now this region lies under water. Now, when the rest of the convection current is acting, whatever event is happening underwater here. Eventually, in this situation, after you pull the plastic scale significantly, after it is getting heated up quite significantly, after that you pull it up, what will happen? It will break. Here also, eventually, as this convection current keeps on happening, what will happen? It will break here. Now, when it breaks, this rising column of heat, now the lithosphere has broken. So rising column of heat is provided by what? The molten materials rising up. That is how the convection current is also enacted. So this rising column of heat by the molten materials rising up will lead to what? In this portion, you will experience underwater volcanic eruption. And there you will come across what? The seafloor spreading that Harry Hess had talked about. So that is how, even in the existing plates, where let's say there is a no plate boundary in existence beforehand, even in that area, due to the convection current which is provided, you can have the mid-oceanic ridges which are created because the water body enters. Observe here, this is the existing plate. That existing plate, which was completely natural and normal, due to the immense amount of heat which is provided from below, that plate starts to thin out. From the top also it starts to thin out. So water body will enter this area and eventually this will break and that will create a new oceanic crust. That is why whenever you come across the oceanic crust, it is very young because it has been created always recently. But the continental portions, the continental crust, they are simply pushed aside or pulled together. They are not circulated like that. That is what explains the aspect that the oceanic sediments, they are very younger. In between, we have asthenosphere also. That is true, Nitin. What role does it play? Asthenosphere also gives rise to convection current in a small localized region, but asthenosphere does not create a convection current which is so lasting enough that it can create that entire movement of continents away from each other. Asthenosphere's role is for the convection current is restricted to a smaller portion and sometimes the volcanic eruptions which happen. We'll come to it by the time that you finish the entire portion of volcanoes. You will understand that. That is what I tried to convey to all of you in the previous weekend as well. That stay through the weekend, pay attention. Trust me, after 2 to 3 modules, things will start getting clearer at a much more significant pace. If it is still not clearer, feel free to ask. So by the time that we are done with the mantle plumes, Nitin, you will have a much greater clue or a clarity about the role played by asthenosphere as well. Okay? I hope that is clear. Now, where is it that you are experiencing this phenomena as of today? In which portion of the planet are we experiencing this phenomena? So as we speak, the land of Africa is experiencing this. It is in Africa where the continent is experiencing that convection current from the interior. And that is why, moving ahead into the future, the shape of Africa that you have been drawing and looking into the map, that will change because Africa will be breaking into two, at least two parts. You have the entire Rift Valley which has been created, and the two different portions of Africa, the eastern portion across the region of Horn of Africa, that is said to be separated from the rest of the portion of Africa. The rest of the portion of Africa will then move to the north, slightly in the northwestern direction. That will close up the Mediterranean Sea. In the coming days, the Mediterranean Sea will also disappear, and that is how the changes are created. Okay? Now, here we come across the types of plate movement. Now, when we talk about the plates, generally they can move only in certain ways, right? So let's say we have two plates. We have the presence of, let's say, two plates, A, B. Now, these plates can move only in a certain set direction. They can either move away from each other, they can move towards each other, or they can move parallel to each other, right? That parallel movement can be like this as well. So away from each other is understood. That convection current will give rise to a movement away from each other. But how is it that the plates will be moved towards each other? So let's suppose we have the various different plates. Let's suppose. Now, let's assume you have two different convection currents. One is here. Let's name the plates A, B, C, and D. And you also have a convection current here. Now, in this situation, A is going to be moving away from B. D is going to be moving away from C. But what about B and C? B and C are going to be moving towards each other, isn't it? Now here, then again, what about the parallel movement of the plates? So let's assume again, you have a mid-oceanic ridge. Let's assume you have a mid-oceanic ridge. Now, in this portion, the land masses, they will be moving away from each other, isn't it? They will be moving away from each other. But these mid-oceanic ridges, they can extend for thousands of kilometers, tens of thousands of kilometers. Now, in that situation, when they are moving for tens of thousands of kilometers, there's a movement. Do you think the rate of movement that you observe here at point 1 and here at point 2, do you think the rate of movement will be the same when they're separated by tens of thousands of kilometers? Obviously not. Some will move fast, some will move slow. Let's suppose in the upper portion here, in this particular portion, you have this plate which is moving at a rate of 5 centimeter per year, this region. And here this region is also moving, but at a rate of 1 centimeter per year. Now, here point 1 is also moving in the same direction as point 2. And both of them are moving in the same direction, but they are moving at different speeds, right? So what will happen? You will have a crack. A crack will be created here. And eventually, right? Eventually, what will happen? You will observe that here, both the plates are moving. Plate A and plate B, both of them are moving, but they are moving parallel to each other. So accordingly, when we talk about the movement of the plates overall, it can be restricted, it can be summarized in three major portions. The plates moving towards each other, the plates moving away from each other, and the plates which are parallel to each other. So how is it that we know that they are parallel to each other, moving parallel to each other? I will take you to the map here. Let's take the case of this map. This is for your mid-oceanic ridge. Mid-oceanic ridge. Now here, this is where you have the mid-Atlantic ridge. Now, the overall movement is away from each other, right? But the rate of movement that you find in the region of Western Europe and the rate of movement that you find in the region of South Atlantic, both of these places are separated by tens of thousands of kilometers. So you cannot have the same rate of movement here, obviously, right? Because the convection current also will not have the equal distribution throughout, because it is not a lab created convection current, it is created naturally. So it will not have the same impact overall. So let's assume here the rate of movement which is observed is around 5 centimeter per year. And here you have 1 centimeter per year. Now, obviously, this is moving much slower, this is moving much quicker. So what will happen? If, let's say, we take a piece of paper and one side of it is moving, other side of it is not keeping up, the paper will bend like this. But the land cannot bend like this. Land is brittle, lithosphere is brittle. So as a result of that, you will observe you have a creation of a crack. So that is where you have the parallel movement which is observed. Okay, and as I was telling you about Africa, observe the shape here, shape of the landmass here, and observe the shape of the landmass here. It is very, very similar. It is as if a kind of a jigsaw puzzle itself. Now, this is where an existing continental plate was divided because of convection current, and water from the surrounding regions entered there, and that is what has created the Red Sea. In the coming days, this Red Sea will further expand due to this movement. And as we speak, there is a convection current which is at play in this region. This is where you have the creation of a convection current. And in the coming years, it is predicted that this will separate, this will move to the north, this will be separated as a new continent altogether. But obviously, in the coming years, by that we mean a very, very long period of time. Okay? That is the aspect of the movement overall. Abhijit, I hope that is understood. So you have different types of plate movements. So convergent plates, plates moving towards each other. So the plate boundary is the convergent plate boundary. Then divergent plates, plates moving away from each other. And when they move parallel to each other, they are referred to as transform plates. Okay, we'll take a look at each one of them with examples, and we'll try to understand the different types of landforms which are created by each one of them. So we start with the aspect of the convergent plate boundaries. Now, when we talk about convergent plate boundaries, this is when the two plates, they will converge, they will collide. Now, depending upon the type of crust that you have, that is whether you have the continental crust undergoing collision or the oceanic crust undergoing collision, the impact will be significantly different. So depending upon the type of crust, the outcome is significantly different. Whenever, in general, in your normal conditions of life as well, because always advantageous to take normal examples. Let's suppose you have water. Now you have one portion of thermocol which is floating, another portion of wood which is also floating. Now if you deliberately make them collide or converge with each other, which of them will go underneath and which of them will ride over the other? Eventually, that is what happens when materials of different densities, when they will come together. One of them will go underneath the other one will ride or climb up. What do you think will happen in this case? Always the denser material, the heavier material goes underneath, right? The lighter material climbs up. Now, in this case also, when we talk about the various different plate boundaries and the various different plate convergences, you will also come across a situation that sometimes the oceanic plate is there undergoing convergence, sometimes continental plate. In that situation, always remember, out of them, which is heavier, oceanic crust or continental crust, which is heavier? Always oceanic crust is going to be heavier. So always oceanic crust is going to subduct. So here, basically, always oceanic crust undergoes subduction. Okay? Always the oceanic crust will undergo subduction. Now, when it subducts, now why is it subducting? Because at two other places, remember that particular portion, you have the various different plates. Let's suppose you have a convection current here and a convection current which is generated here as well. So as long as these convection currents are in motion, the collision will continue to happen. The convergence and the subduction will continue to happen. So that is why this convergence that you see will continue as long as there is a convection current which pushes them towards each other. The moment this convection current disappears, the subduction also stops, or the movement also stops. Now, depending upon which crust is there, which crust undergoes the subduction, you have different kinds of events which unfold. So why is it, or how is it, that plates, they subduct, right? So here, rather than subside, let's talk about subduct. How is it that the plates will undergo subduction? So here, when we talk about it, let's suppose we talk about the oceanic plate and we talk about the continental plate. We'll study about oceanic continental collision in greater detail, don't worry about it. But here, let's suppose you have a continental plate and an oceanic plate. Oceanic plate is going to be the heavier one, despite being very thin. Due to very high density, it is going to be the heavier one. So oceanic plate will undergo the subduction, right? While the continental plate will be on top. Now, after a point of time, when significant portion of oceanic plate is hanging like this, it is not hanging in free air, it is going into the portion of asthenosphere, where some portion of it will be partially molten, right? Partially and significantly consumed in the region of asthenosphere itself. Now here, as it is hanging down, it will basically feel the impact of gravitational force. Here, take the example of the toy train. When you keep a toy train, I'm sure you would have seen toy train or played with toy train in your childhood days. So when you keep a toy train on the table, it is very stable. It is as if there is no issue with it. But do one thing, take it to the edge and hang out the portion of one of the portions of the toy tray. Hang it out over the table. You will observe that the rest of the train is also pulled by it. Why? Because the gravitational component is significant when something is hanging vertically. So here also, it will experience that kind of a pull due to gravitational force. And that pull which will be initiated due to that subducting plate will pull the rest of the plates as well. So that is what is referred to as slab pull. That is what is referred to as slab pull. I will write the definition also before you panic. So this is basically the movement of the plates towards the point of convergence initiated by the already subducted portion and overhanging portion of the plate. Okay, that is what is slab pull. Now this plate goes underneath in the portion of mantle. After reaching a depth of around 160 to 200 kilometers, it experiences the heat, extraordinary heat of asthenosphere. And that is when it starts to melt. That is when it starts to get converted into molten form. And that is how eventually the entire crustal portion is circulated as well. The oceanic crustal portion is circulated, where the older crust, they meet the region of asthenosphere. And by newer volcanic eruptions, new crust is created again. So let us take a look at the various different types of convergence or collisions which can happen. Now, when we talk about convergences, there can be three types of convergences: oceanic, continental, and oceanic continental. Because you have oceanic crust and continental crust. So eventually only these three types of convergences will happen, right? So let us take the case of oceanic plate and a continental plate. Here you will find multiple such examples of it. I'll take you back to the plate boundary so that I can indicate to you where this is happening. So in this particular portion that you observe, that is the minor Nazca plate and the major South American plate. Here you have a convergence which is happening, right? Even in this particular portion, you will observe Yuan, the Fuca plate, and the North American plate. Convergence is happening. In this portion, you will observe convergence is happening. So like that, convergences are happening between ocean and continent in different areas. We'll take the example while we are talking about of the Nazca plate and the South American plate in general. I hope again, I will take you back. I hope you are able to look at it, where this is happening. Now, after this, when I talk about the example, so here, let's assume you have a continental plate and you have a oceanic plate. Example, we can take the case of Nazca plate and South American plate. Okay. Now here, what do you observe? You will come across a scenario where, let's say, you have the very thin oceanic plate and you have the continental plate, significantly thicker continental plate. Now this portion is underwater. Significant amount of water is present here. Now both these are moving or are being pushed towards each other due to convection current, which is happening somewhere else. Now at the boundary region, the heavier plate will undergo subduction. Which is the heavier plate? The oceanic plate here. That will undergo subduction here, right? So what will happen here? In this portion, subduction will happen. Now, as the subduction is going to happen, do you think it is going to be absolutely smooth, like one portion is there, other portion simply starts sailing around or simply starts moving around? No. You have all these which are made up of kilometers thick rocks, right? The lithosphere is the upper portion of crust along. The lithosphere is actually the entirety of crust along with the upper portion of mantle also. So these are very significantly heavy rocks that we are talking about. Now, when they are made to rub against each other, obviously the movement is never going to be smooth. It is going to be staggered, that maybe some movement happens, then the potential energy keeps on developing, and again some movement happens. Then again the energy keeps on developing, again some movement happens. So that is where it is going to be a kind of an irregular, staggered motion which will be observed here. Now, also, the continental plate, which is lighter. Now, here, let's suppose this is the continental plate. As this undergoes subduction underneath, this will start accumulating the materials due to the force of subduction. The materials will start accumulating here. It will get deformed at the point of subduction as well. So that is what is observed, that at the point of subduction, first of all, there is a significant amount of deformity created. So the continental plates, they get deformed. Now, when they get deformed, also, as the oceanic plate is pushing towards the continental plate, due to the resistance, there is a kind of accumulation of materials as well. So materials will get accumulated in the form of a fold mountain right at the edge. Right at the edge of the continental landmass, you'll find the fold mountain. Now here, in that immediate portion at the point of convergence, you'll find that there has been creation of a depression. And this is what we refer to as an oceanic trench. Oceanic trench. This is what is referred to as a fold mountain. Okay. Now, furthermore, as this motion is happening, this motion is never going to be smooth at the point of convergence. This motion is never going to be smooth. It is going to be anything but smooth, very rough. When it is moving suddenly, after overcoming all the obstacles, it indicates a movement, then it waits or stagnates. Again, sudden movement, again, there is a stagnation. So, due to this, you have, whenever there is a sudden movement, there's a release of massive amount of energy. And that energy is so massive enough that it can shake up the ground surface also. And that energy is what we experience in the form of earthquakes. So in this entire region, you will experience, as the plates they rub against each other, here you will experience earthquake zones. Earthquake zones. Now, as this starts moving further to the depth, it will experience greater amount of heating. Now, greater amount of heating would also mean what? Materials would start to melt. Now, when we say the materials will start to melt, which are the materials which will melt? The plate, the oceanic crust, right? That will melt along with the some amount of sediments that it would have carried along with it. That would also melt. And because it is an oceanic plate, as it is subducting, it will carry some amount of water also. Some amount of water will also be carried to the depth. That will also undergo melting, isn't it? That water will also melt. Or when water basically is heated, what happens? It gets converted into water vapor or gas. So at the depth, now you will have the concentration of molten materials and gases as well. Now these molten materials, here, materials will melt, and water vaporizes due to high temperature. This happens at a depth of around 160 to 200, sometimes even 300 kilometers and more. Now, these molten materials, they will be very hot. They will have the presence of gases. Gases will always try to rise to the top. So all these materials, they will try to rise up. They will try to rise up. Now, since they are very hot, they will melt the portions above it as well. They will rise up. Now there is, as long as the convergence is happening, the supply of these molten materials will keep on happening, right? So more molten materials will rise up, pushing the earlier materials further upwards. Eventually, they will break from the surface in the form of volcanic eruption. Volcanic eruption. So that is what happens whenever you have a continental oceanic convergence, while the oceanic landmass or the oceanic crust and the oceanic plate simply straightforward undergoes subduction because it is the heavier one. The continental plate, which is the lighter one, first of all, it will experience a kind of a folding at the coastline, leading to the creation of the fold mountains, and the molten materials, they will move up in the form of volcanic eruption. And at the point of convergence also, you will have a kind of a staggered movement which will initiate earthquakes as well. So that is where you have the entire process happening. I will repeat the entire process. Listen to this. So here initially the oceanic plate undergoes subduction. As it is moving in this particular portion at the boundary, there will be a deformation leading to the formation of a trench. But this movement will also not be smooth. It will be very staggered, leading to causation of or release of energy that shakes up the surface in the form of earthquakes. Now, as this plate goes underneath, it will carry some amount of sediment, some amount of water as well, because it is an oceanic area. So some amount of water will also be carried by the plate. Now, upon reaching a depth of 150, 160 to 200 kilometers depth, the temperature will rise up quite sufficiently because that is the region of asthenosphere. So the temperature will rise up quite sufficiently, due to which the materials will melt and water vaporizes. Now, that water vapor is a kind of a gas, and that gas and liquid also will always try to rise up because it is lighter, it has got greater energy. Now it starts to rise up. As it rises up, the pressure of the gas will help it rise up, but the molten materials will provide the heat which will start melting the materials above it. Now, as long as this convergence is happening, you will have a continuous supply of these molten materials as well. Eventually, they will break the surface and they will cause volcanic eruptions. Okay, that is the oceanic continental convergence. Example of this. For example, again, I will take you back to the same image. So here you will observe that off the coast of South America, here you will find a very deep Peru-Chile trench, which is around 8,000 meters deeper from the sea level. That Peru-Chile trench you will find here. Here you will find the presence of fold mountains in the form of which mountain chain? Yes. Here you will find the Andes. The Andes mountain chain you will find to be present here. It is here that you will find volcanic peaks as well. For example, you will have Mount Cotopaxi, Mount Aconcagua, various different volcanic peaks. Similarly, in the case of North America, here you will find that North American plate is also moving in this direction westwards. That is where it is riding over the Pacific plate. Pacific plate is undergoing subduction. So here you will find the presence of the fold mountains in the form of Rockies. It is in this region where the newest fold mountain of the world, the youngest fold mountain of the world, that is to be found. And that is the Cascade Ranges, which have been formed right here. I will give you the map pointing after the class. You can locate it after the session. And here also, you'll find various volcanic peaks and volcanic eruption. For example, Mount Hood, Mount Shasta, Shastina, Mount Rainier. All of these are the volcanic peaks which are observed in these areas. So that is basically the scenario or the situation of this kind of a convergence. Example, Andes. Example, Mount Cotopaxi. Example, Peru-Chile Trench. Okay, these are your examples of all of this. Okay, now we come across, yes, Fujiyama can also be considered as an example. So now we come across another type of convergence, that is where the oceanic and other oceanic plate will meet. Now, in this case, which of the plates will undergo subduction? If both the oceanic plates are meeting, which of them will undergo subduction? Always the older plate undergoes subduction. Why? Because the older oceanic plate will always tend to become significantly heavier, right? Why? Because over a period of, let's say, millions of years, there would have been significant amount of deposition of sediments which would have happened. Many different compounds would have formed oxides. They would have trapped carbon, oxygen, and that is where different compounds would have been created. That is where the older plates, they become heavier. Now, where is it that we experience this? A kind of an oceanic convergence. In which part of the world? So it is experienced in the region of Pacific Ocean, especially the region of Western Pacific. Now, in the region of Western Pacific, if I can take you back to the slide again, here, observe this kind of a convergence which is happening. Observe the convergence happening here in this region, the convergence happening here also. Right? In these portions, you have a significant amount of oceanic convergence which is happening. So what happens because of that? Let us come to that portion. that what happens when you have that kind of a convergence. The principle observed and the principle followed is very similar, even in this case. What is the principle? The heavier plate will subduct. But as the subduction happens, that subduction, is it going to be smooth? No, because you have crustal portions which are rubbing against each other. Will there be deformity at the point of convergence? Yes. As is the case earlier, here also deformity will happen. Now, in the earlier scenario, you had a continental crust. Continental crust, when it experienced the resistance from the moving oceanic crust, it started accumulating and it folded. But when we talk about oceanic crust, it is very thin. It cannot get folded. It cannot have the accumulation of material. So that will be the difference in between these two areas. We'll take a look at it. For example, here, let's suppose you have one oceanic plate. You have other oceanic plate. Let's suppose this is the older one. And also the heavier one. Now here, all of this is happening underwater, by the way. All of this is happening underwater. Right? Now, at the point of convergence, there will be significant amount of deformity. As it starts to converge, there will be significant amount of deformity. In this portion. So here also a trench will be created. Oceanic trench. And you'll find many examples of this. Most of the trenches are found in this category. So you will have Mariana Trench, the deepest trench of the world. Mariana Trench. You will also come across Tonga Trench. These will be the example of your various trenches. Here also, in this particular portion, the movement will never be smooth. So these will also form your seismic or earthquake zones. Or earthquake zones. Okay? And basically, as it starts to significantly subduct, it will melt upon reaching a depth. It will carry some water also. Some amount of water will also percolate in this region. That water will also basically seep into this area as it undergoes melting. Now the molten portion, along with the vaporized water, will try to rise up. They will try to rise up and they would give rise to underwater volcanic eruption. Many of the times, this underwater volcanic eruption will lead to creation of underwater mountains also, what are referred to as sea mounts. In many of the places, these sea mounts, they have a significant amount of height. They can be 3,000, 4,000, 5,000 meters in terms of height, but they never appear over the ocean floor. They remain underwater because they are attached at the sea floor, right? That is why a few of the underwater mountains, they have a height of around 8,000 meters from the seafloor. Imagine if this would have been above land, it would have been one of the tallest mountains in the world. But they are underwater. They don't even appear above the surface. So that are the secrets which the oceans hold. Now here, basically, it will lead to creation of underwater mountains. Many of these underwater mountains, they come into existence. Their height does not increase because let's assume the convergence stops. It does not proceed anymore. So no more volcanic eruption. So the height won't increase anymore. So this will be restricted to an underwater mountain. And that is, underwater mountain is what is referred to as a sea mount. That is what is referred to as a sea mount or a sea mountain also. Now here, eventually, if let's say the convergence continues to happen, molten materials will continue to be provided. And here, eventually, the size will grow larger, larger, further larger, till it breaks through the surface. Now, when it manages to break through the surface, that is when you will observe the formation of what is referred to as an island or a kind of a volcanic island. Okay? When this will break through the surface, that is when you have formation of a volcanic island. Okay? So across the oceanic convergence, that is where you will find the formation of many of the islands. Group of islands are known by what particular name? When we have a group of islands in a particular place, what is the name associated with those group of islands? Let me see. Very good. It is the archipelago, right? So group of islands that are referred to as archipelago. Let me write it here. Group of islands taken together, that is what is archipelago. So that is where at the point of convergence of the ocean and the other oceanic crust, you'll find many of these archipelagos. For example, take the case of the Indonesian region. Hundreds and thousands of small islands. Take the case of the region of Philippines. Hundreds and thousands of islands. Nearby those areas, you will find a trench also. Near that region, you will find seamounts also. Near that region, you will find volcanic eruption also. So that is what happens in the case of oceanic convergence. Okay? Is that understood? Or is there a doubt which prevails? Let me know. So when you put it here, this is where you will find the deepest trench of the entire world, that is the Mariana Trench. Okay? This is where you will find the Tonga Trench. This is where you will have the volcanic eruption. In the region of the Philippines, you will have volcanic eruption in the form of Mount Pinatubo, one of the most significant eruptions. And here you will find Mount Tonga, the Tonga eruption, very famous eruption which happened in 2022, January 2022. So that is the outcome of it. Okay? Why the older oceanic plate is heavier? That is because when we talk about the oceanic plate which has been formed, let's say 400 or 200 million years before the new other one or the newer one. So in those 200 million years, there would have been significant and substantial amount of sedimentation. Those sediments would have formed multiple sedimentary rocks that would be associated with the oceanic crust itself. Then the oceanic crust would have reacted with the water and oxygen present in water, the carbon dioxide, etc. It would have formed various oxides and carbonates. So all of that basically would have made the older plate heavier. Okay. Namita, this movement of plates are regular, or what initiates this movement? So this movement is initiated by the convection currents. So the convection currents that you find to be present in the region of the mantle, that is what gives rise to the movement. Where does that convection current of the mantle come from? From the heat supplied sporadically or in a kind of individual manner, in a kind of a differentiated manner from the region of outer core. You have a lot of residual heat which is supplied. That residual heat gives rise to those convection currents. And that convection current gives rise to movement. I hope this is understood. They are irregular. Convection currents are highly irregular. So they can come into existence in a region. They can basically come into existence for few million years, few 100 million years, and they can disappear. I will give you the example of that as well, about the older convection currents, and which will help you understand. Utkarsh, there is any chance that lighter one subduct due to any cause? No, lighter one does not subduct. So I'll give you the example of how the convection current changes. So basically, this is the present movement. Now, at one point of time, imagine it if you can, at one point of time, this North American plate had collided with the Eurasian landmass. That is what gave rise to the Appalachian Mountains here and the Scottish Highlands here, what are referred to as the Hercynian mountain ranges of that period. So it gave rise to the mountain formation in this entire region, because at one point of time, convection currents were driving these two places together. That is what led to the folding. And observe that the convection current, the region where this is happening, significantly changed, where now they are moving away from each other. Right? So that is how you have the changing convection currents. Convection currents are not always going to be fixed, but also you have to think that when we think about it from the human perspective, we will never think about it in millions of years. So when we say irregular convection current, even though they are in existence for a short time, but that short time can mean few 100,000 years, few million years, and so on. As of now, think about it, a convection current has erupted underneath here in Africa, and African landmass is splitting into two. So it can come up anywhere. Okay? I hope that is understood. Okay? So now we will take a break. After break, we talk about the continental convergence, and then we will talk about the formation of Himalayas, that what kind of convergence and movement led to the formation of Himalayas. We'll take a look at the other kind of plate movements as well before entering into earthquakes and volcanoes. So we take a break, and we will be back by 3:50. Okay, so take a lunch break till 3:50. Shubhajit will come at the divergence. So when the divergence happens, there's creation of a newer crust in that region. And it just like in the case of seafloor spreading, we had seen that newer crust that again gets divided, again newer crust, again it is pushed aside. Something of that sort happens. Okay, so let's take a break. We'll come back and then we will continue.